Okay. Good morning, good afternoon, good evening. As this is a global event, we have people logging in from the various parts of the world, right? Particularly from India and US and also Canada. So my name is Jayanta Lahiri. I will be your host for the day. I'm a I'm a Shibpur alumni of 1986 batch in electrical engineering. I have been in this semiconductor domain for the past 35 plus years. That also tells my age in a way. So currently, I live in California and work for a Taiwanese semiconductor IP company by the name of M31. Prior to this, I worked at ARM, Global Foundries, and TI, amongst others. So this is the first session of the Semiconductor Special Interest Group. We plan to host roughly one event a quarter. We should be mostly through this sort of a webinar. So today's topic is semiconductor ecosystem. And we are privileged to have two very accomplished panelists today. And of course, they're much younger than me. And let me introduce my fellow panelists. So first we have Tapas Nandy. Tapas, can you please wave your hand so people know that who you
Oh, hi,
are?
this is Tapas.
Okay, yeah. So Tapas did his undergrad from BE College in 1988 in electronics and telecommunication. He had a long stint at ST Microelectronics, Noida, and currently he works for Intel Bangalore, leading the interface IP development. He's definitely an analog guru. Our next panelist is Sumit. Sumit, can you please wave your hand? Yes. Sumit is a graduate from Bay College in 2000 in electronics and telecommunication. He works for Qualcomm, where he leads the design flow, methodology, ED, and physical implementation. Before Qualcomm, Sumit was at Intel and Synopsys. So what we're going to do is we are going to get started with few slides to introduce the topic, right? Uh, can we put everybody on mute? Yeah, yes. So I think we'll go through a few slides to introduce the topic, and then at the end we'll take some questions, and we'll see how it goes. You can also use the chat box to write your question so that I will pick up some of those questions, and then we'll open the floor also for people to ask live question. Okay, so Shumit, if you can please share the slide, rather Taposh, can you please?
Yeah, I can share the slide. Just let me know if it's visible for everybody.
Yes, it is. Okay.
I give you the control.
Yeah, but you need to forward the slide.
Yeah, I'll do that. And what I'm doing, just making it so that you have a laser pointer, you can control it. Just
Yes,
check whether you're
thank
able
you.
to.
Yes. So while we get started, so I think I see in the WhatsApp group there are 200 plus members, right? Which is a very good number. I hope we can create some interest in semiconductor. And my target audience will always be both the students of the IIEST, right? And also young professional who are getting introduced to this domain so that they can learn and continue to grow in their career. That's the aim we have for this special interest group. Next slide, please. Yes. Yeah, I will just introduce the topic and then I will hand it over to Taposh and Sumit, who are experts. Yeah, so if you look at it, this is semiconductor in your daily life, right? So everything that we use, right, whether the cars we drive, whether it's a TV or a fridge or a laptop or a food processor or our cell phone, right? Each of these appliances, right, have major semiconductor components for its functionality, right? There's a control or a CPU that all these chips have, and all those are piece of semiconductor. And if you remember during COVID, particularly during the second year, 2021, with everybody working from home, so everybody needed a laptop or a cell phone, right? And also a car. And there was a huge shortage of semiconductor chip, right? So that's how important semiconductor is in our daily life. And since then, there is $100+ billion of investment is happening across the world to boost wafer production. So some of the terms that I'm going to use and other panelists might be a little bit new, but don't worry. As we go through the year, as we go through this journey, I think all of us or all of you should become much more acquainted with some of these terms, right? So yeah, if you don't understand some term, just write on the chat box, and at the end, we are more than happy to explain or expand. Next slide, please. Yeah, so these are some of the pictures that I took from the TSMC symposium that happened in here in California. So TSMC, as you know, is the biggest manufacturer of semiconductor, right? So they own almost 60 to 65% of the whole business in terms of number of wafers that get processed, right? So TSMC's projection is by year 2030, the whole semiconductor ecosystem will be more than $1 trillion. And today it's like 750 to 760 billion US dollar. And on the right hand side, let's look at some of the growth stories, right? So the biggest growth story obviously is AI, right? So there is, I mean, we don't need to talk about it, right? I mean, there's so much of going on with generative AI. And if you look at the Microsoft or any other thing, whoever, chat box and this and that, all that is software, the companies that work on it, but the underlying there is a AI engine, and most of them actually comes from Nvidia, right? So the growth story is in 2024, the AI related semiconductor systems will grow by 2.5x or 250%. PC and smartphone, they are a little bit saturated, right? So they will grow at 1 to 3% this year. And automotive, it had grew a lot in the last 2 years, but this year is not going to be that growth phase in automotive. There's going to be a little bit of a negative growth, like -3 to -1%. And IoT, Internet of Things, which of course encompasses everything, whether it's your fridge or whether it's your TV or whether it's some of the switches that we have, all those are IoT application, right? So that will continue to grow at 7 to 9%. In the bottom, what I have put together is definitely TSMC's technology map, right? Of course, you need to understand, and in terms of there is a way back in 1960s there was a Moore's law, right? That Andy Moore predicted that every 2 years the technology is going to change, and the number of transistors, let us say per square mm, is going to double up. So effectively, the feature size is going to become like zero point 0.7 or something. And then if you multiply zero point 0.7 by zero point 0.7, you get like half, right? So the number of transistors will actually double, right? And this is what this graph shows, right? We are currently at, let's say, 5 and 3 nanometer, right? If you look at 2024, you are like 3 nanometer, right? And to give you some perspective, when I started my career in semiconductor in 1988, the feature size was 3 micron. So over the generation of more than 3 decades, from 3 micron or 3000 nanometer, the feature size today is 3 nanometer. And it will continue to progress. And the roadmap is by next year, we will have 2, and then we will have another version, the improved version or performance version of 2 nanometer. And by 2027, you see a number which is called A16, because we don't, I mean, it's like, another division, right? It's like angstrom. We were at nanometer, and now we are going to the angstrom era, right? So that's why suddenly the number has increased, A16, but effectively it is like you can call it 1.6 nanometer or something. That's how the technology is scaling over the years. Next slide, please. Yeah, so these are some of the end market usage, right, of the semiconductor, right? The first one is automotive. So if you look at automotive, the all the sensors, right? They're all semiconductor component. And today, there's a lot of autonomous driving in car. All that is semiconductor in there, right? So automotive is one segment, and automotive requires some very high class, quality as well as the temperature, right? Because it's the car will be heated if if you're driving your car in 50 degrees Celsius in Delhi or something, right? So we need to ensure we do design that can withstand the high temperature. So there are like temperature specific, auto grade 1, auto grade 0, which can go up to the junction temperature of the devices can go as high as 150 degrees Celsius. So it's a high margin but low volume space, right? Because of the amount of quality checks you need to adhere to. And then there's functional safety and other things. So this automotive sector, they take semiconductor from 7 nanometer to 55 nanometer. Then we have the wireless, and wireless is your cell phone, right? So cell phone has semiconductor features that is from 3 nanometer to 130 nanometer. So there are CPU or GPU running at 3 nanometer. There are display driver, the display that runs at 28 nanometer. And then there's the audio amp or the speaker that you have, right? The speaker or the microphone that runs at 55 nanometer. Then is the IoT and mass market, right? So this is pretty huge. It's very high volume, but the chips are very inexpensive, and it encompasses tech node from 180 nanometer to 22 nanometer. These are low margin design, but very, very high volume. The fourth is the high performance computing or server, right? All our cloud application runs there, right? So whether it's a Google Cloud or a Microsoft Cloud, all of it runs on, what is called HPC, high performance computing and server. So they run absolutely on the cutting edge of the technology, and 3 nanometer and 5 nanometer. And all these semiconductor chips are provided mostly by NVIDIA, AMD, and Intel, right? They are the leaders. And then there are high-speed links for communication, and now there is a new thing called chiplet, where you divide and conquer. You divide different functionality in different chip, and then in a common way, you sort of you do integrated that, right? So we'll talk a little bit more on a later time. So this is the end application, and then we'll start deep diving in some of these end application and how the ecosystem work. Over to you, Sumit.
Thank you, Jayanta. So let's move on to the next section. So after the introduction, I'm now going to talk about what does it mean that EDA, the semiconductor ecosystem, what are the different components? And in next section, me and Tapasda, we are going to talk about that, and we are going to go into a little bit more details about it. Let's go to the next point, please. Okay, so if you look at the overall semiconductor supply chain, it is a pretty large. And now you can divide this entire supply chain into two parts. Number one, what we call it as a front-end design. That means all the design houses, they are making various kind of chips. And the second is the manufacturing. Now, if you look at the global economic position, this design part is distributed all across the globe. And the manufacturing is restricted on the certain part of the geography. And nowadays you can hear that that is one of the fundamental reasons for the geopolitical tensions. So today, if you look at the top portion of the graph on the left side, you see EDA and the core IP. So you need an assisted software to design these kind of very complex chips. Like Jayanta mentioned about the 3 nanometer design, if you see that the number of transistors getting used those point of time are quite limited. Versus if you look at some of the AI silicon, there are like 54 billion to 60 billion to 80 billion transistors on that. And definitely you cannot do a hand design or very manual design on that. You need an automated software to do that. And to do that, EDA software industry was created. They create the software which gets used for doing the chip design. Now, more and more designs become complicated, then people realize that some of the basic fundamental design, like for example, I need a CPU, I need a GPU, like that cannot be done independently and in isolation. So why don't we create that as a commodity? And that's how the core IP business has started, where people do that. They create some fundamental design like CPU, GPU, graph, then DSP, and a lot of other things, and that become a commodity and gets sold. Now, if you look at the chips today getting world in the semiconductor system, you will mostly get three kind of design. You have a logic chips like any microprocessor or any control system chip. Those are kind of the logic design. Then the second part is that DAO, which is discrete, analog, and others. There are a lot of other kind of things like we just talked about the speaker amplifier. We just talked about the display drivers. Similarly, there are a lot of analog ICs exist in the world. Like there are those ADCs, DACs like that. So that is the second market, and the third one is the memory. So if you follow the Van Neumann architecture, based on that, the entire design is calibrated, like one block is doing the calculation and it is all written in the memory. So the demand of memory is there since 70s and it is just going increasingly high. We are going into the different standards. And the memories are also, you need the volatile memory and non-volatile memory. So this is like another fundamental block which is making a huge business. If you come to the equipment side, the equipment and materials, the basic silicon wafer supply comes from certain companies, which is getting used for manufacturing, followed by packaging by using plastics and others. And those equipments, which is actually printing that 3 nanometer, what just we discussed in the previous section. And day by day, this manufacturing is becoming complicated. And this is right now dominated by few countries in the world, but not. And in the right side, you can see that how is the countrywide domination. So EDA core market, mostly the American companies are dominating. IC design is kind of distributed, but still a lot of American companies are taking part on that. Discrete and analog, you can see that the Asian companies have a lot of dominance on that, and memory is dominated by the Asian companies. All those Samsung, SK Hynix, those kind of companies in the world. If you look at the equipment side, it is kind of equal share between Asia and US. Similarly, the materials, wafer fabrication also, you can see that because a lot of the production is happening in the Asian countries. And so the surrounding ecosystem and the vendor system was also evolved in the Asian countries. Let's go to the next point. So this is the, after that view, let's look at that what are the various opportunities we have in the semiconductor industry. So if somebody, some student want to come to, let's say, semiconductor industry, what are the different sectors they can get job? And next subsequent sections, we are going to talk about some second level details of this individual bullets, what you see. So the very first one is talk about IP core. As I said that every company cannot design each and every small building block. That could be a NAND gate to a CPU core. So this particular ecosystem got evolved where they say that, okay, I'll make a CPU core, a general purpose CPU core, you can use in your product and you pay me a royalty. Similarly, I can make a SRAM and that SRAM can be used in your design and you can buy that SRAM design circuits from me, and then based on that, you can make your chip and you pay me some money for that. And that's how this industry evolved. There are many companies. Our panelist, Mr. Jayanta, he is one of the IP core company. He comes from that background. He is designing IP core for various segments, and these fundamental blocks are key essentials. So there are some special circuits also like CPU, GPU, ISP. ISP is that the sensor processor for the camera processing. SerDes is all the serial design interface which gets used in the various form like DDR, like many other cases also. Now the second industry, which is EDA, electronic design automation. As I mentioned before, this is another integral part of our design ecosystem. As our designs are very, very complicated, it's a manual design is no longer an option. You need a automation, you need a tools to do the design. Sometime in 90s, there is the concept came up that can I write my design behavior in a very high level language like Verilog or VHDL, and then I synthesize into circuits and gates. And that is kind of a start of this. And before that also, the simulation in the analog domain was there for some time. And this is how we are synthesizing a circuit. And after that, it went on and on. And all the modern days, like 3 nanometer or 4 nanometer, without this, there is no way manually possible. Can EDA solve my problem 100%? Answer is still not, because the technology is so complicated. You need a lot of manual intervention as well as EDA tool to solve a problem. Some of the examples are schematic, spice simulation, logic simulation, synthesis, place and route. So this industry, which generates actually the software which is used by the core companies or SoC companies. Next, number 3 is the SoC, system on chip. Many calls it as a ASIC company, many calls it system on chip company. So what they do is that they design the SoC, which finally goes and sit on an electronic product. So they use the EDA tools, they use the IP cores, and finally generate a system on a chip. And that chip gets used on various equipments like your cell phone, like airplanes, car, and so many different places. Now the system on chip companies may have their own fab where they manufacture the chips, like company like Intel, Samsung are such examples. And there are certain companies like Qualcomm, Broadcom, Nvidia. What they do is that they do the design and send to the general purpose fabrication companies like TSMC and others, and there they get manufactured. Third one is a fabrication. These are the factories. The factory, it is like any factory production line. So the design comes and it goes to the various section of the factory, and finally the finished product, which is a SoC, comes out on that. Design companies like Intel, Qualcomm, Broadcom, Nvidia, Apple, this all send their design to these companies, and then their final product is a wafer and a cut wafer, and that wafer will be packaged and that will become one chip which will go to your product. Now, finally, next one is assembly and test. After the fabrication is done, you need to ensure that it is tested before you put it on an electronic product. Why do I need that? Today, if I take a SoC, which is like 50 billion gates, and there are 10 gates are faulty, and it is a manufacturing defect, if I don't test it, and if I put it on a product, right, think about it in a very expensive car, and the car malfunction because of that, and that is a very, very big risk. So upfront, we need to figure out the faulty parts and we need to throw them out. So there is one industry got created like that. We call it as a OSAT, or there is an integrated tester houses are also there. What they do is that they take the package part, they put it on a tester, they test it out that whether all the gates are fine or not. And finally, if everything comes out fine, they just push it in for the next production line. And there are a lot of technologies, a lot of algorithms, a lot of ecosystem got developed to do this OSAT. And now this is one of the booming field in India. There are a lot of investment also coming in for this assembly and test side of it. So once another test side, sometime this packaging industry comes along with the assembly test, sometime it comes separate. What they do is that they take the bare die, silicon die, they put it inside a package, and that overall package part comes out. And that because we do not put a bare die silicon onto a system or PCB, it gets packaged first, and then the packaged part come over there. Now next comes another important thing called firmware software. Olden days, if you remember that, what we used to do is the fixed function hardware. So consider this way, we have a chip which does only a specific function. That could be a multiplier. I just give two number A and B, it just generate an output, what is A into B. But nowadays, it's a more and more general purpose hardware came, the programmability become a big field. So that means I have a general purpose hardware where the registers and the programming space is given to the user. User can configure the hardware and based on that use for their need. And that's what created the firmware and software industries. And this is where we develop OS like Android, like iOS, like Windows, Linux, various things. And a lot of application software comes over there. And they conform standards, right? Now, when the OS comes in, like Windows, Linux, Android, they have certain expectation, the way overall stack need to be developed, what sort of APIs need to be given, what sort of board level service pack or BSPs need to be coded. So all those things are done, then they give an open platform where user like you and me can go and they can code something. You already are using a laptop or a phone. This is a classic example. In your phone or laptop, there is a Windows or Android is running. And that is the example of these firmware and software companies. So in this industry, you need to understand the hardware and their behavior. And based on that, you have to design a software which runs on that hardware. And finally, the electronic system design. So this is the end product development system. We have a chip where we have a motherboard. Now we package it in a mechanical package. We house it inside one item and we create the functionality. Take an example of a car. The entire car consists of various mechanical parts, and the control of many of the parts is controlled by that PCB or the central computer or TCU, telematic control units, or IVI. Those things are the electronics part of it. So here you can see that there is a mechanical portion and electronics, they come together and they create the final products. So there are many companies who is the actually buying the electronics, buying the mechanical products, and finally creating these fabulous electronic gadgets, and that we are using in a daily life. Take an example of your digital camera, take an example of car, and so many other things in your daily life. So this is a very high-level overview of the overall industry. And now we'll go some little detail of each and every portion. Next file, please. So now if you look at it, what are the companies? If you just try to map it out and see that what are the different companies in the world which can create jobs and how do they map to the set of things what we talked about in the previous slide. You can see on the left, on the material side, there are a bunch of companies. There are like DAQ, BASF, UCT, like that. Equipment side, ASML, Applied Materials, these are quite popular. EDA2, Synopsys Cadence, Siemens Digital. A lot of companies are there which are making their own chips, right? You can see Intel, Toshiba, Qorvo, Microchip. There are so many guys are there. There are foundries like Intel, Samsung, TSMC, Micron. They are the manufacturing thing. As I talked about, there is a fabless semiconductor company, Qualcomm, Broadcom, AMD, NVIDIA, all of them are there. So you can see that the industry is distributed across so many different parts, and that we just talked about in the previous foil. And here are the different companies, and many of the brands are very well known in the world. And I'm sure that all of you heard about NVIDIA, Intel, Qualcomm, and all, and this is the exact work they are doing. So if you are a student and if you are looking at an opportunity, this is your opportunity space where you can fulfill your dreams in this field of semiconductor. Okay, let's go to the next file, please. Now let's talk about various part of the industries. The first one, we're going to talk about the EDA industry, what EDA is all about. If you look at the size of the industry, it is growing about 19.16 billion industry going to be 2028. This is one of the Blue Wave Consulting, their data about the industry growth point of view. Now, what are the products? As I mentioned that EDA company generate a software, and this software run on a very heavy compute system like a like HPC we talked about. These actually are the HPC product. This software run on a high performance compute, and it generate a lot of various design collaterals which typically go used for the design process. Now, if you look at some of the products like synthesis, place and route, then logic synthesis, then STA, all that, analog side, SPICE, layout editor, schematic editor, system C, all those different kind of tools come over there. What are the companies like Synopsys, Cadence, Siemens Digital, ANSYS, Keysight, each and every company innovating on their space. On a daily basis, design companies generate problem, and those problems is actually solved by the EDA companies. Take an example, when very early 90s, somebody thought about productivity. They said that, can I write a behavior of a chip in a very high level language, and that language is very log? And can I synthesize two transistor level circuits from there? And that's how the synthesis tool was born. And today that synthesis industry is a pretty huge industry. Synopsys got Fusion compiler, Design compiler, then Cadence got Genus, Mentor got Oasis. There are a lot of different companies are there which is doing that. And after that, the next problem statement comes that, hey, you have given that the circuits, but once I place it on a die, I cannot meet timing. There is I don't know that two gates should be next to each other or far from each other. And that's how the placement industry was born. So it is more of a problem solving industry. If you want to get into that industry, you have a digital electronics, computer science, computer architecture, EDA algorithms, which is very key. These are the skills you need to have. If you're expert in one of such skills, you can definitely aspire to go into EDA. I started my career straight out of BE college, and I joined Synopsys. That was my first company, and this was like entering into the EDA market. And I was amazed to see that the lot of technology is getting developed day in, day out. Let's go to the next one. Next, we'll talk about the system on chip, or SoC. This is the fundamental part. My current company, or Tapas's current company, Intel, and my current company, Qualcomm, where we are developing chips. Now, different people have a different market segment targeted chips, because the kind of engines we need to put on a SoC will vary depending on the market. If you look at the SoC market, it is like a $550 billion market based on the SIA report last year. And in this case, if you see that the growth is phenomenal, growth is happening. Right now, it is a $550 billion industry. It is growing at a quite rapid pace. And if you look at some of the growth drivers, it is telecom. Telecom side, there are processor, network processor, modem. Modem is a one key fundamental item which is changing the telecom products. You all are using a 5G phone. You know that the 5G innovations comes from this modem in the telecom sector. Then next is the HPC. You are all using the microprocessor for server or cloud like that. Your photos are going to Google Cloud. Whenever you are searching, it is coming up, and that cloud is actually where the HPC are getting used. These are the very fat and big, powerful server processors having a lot of horsepower on that on running, and some of the Intel, AMD, they are the key players, and the GPU space, NVIDIA, AMD, they are the key players who are making it. Now, more and more advent of AI ML, now there is no longer general purpose processors are required. And now we need a dedicated hardware, like the problem solving I was talking about past, that I figure out a new use case, what sort of hardware I can design. So there is a new market created where I have a neural network. I want to map the neural network on a chip, and that chip will very fast operating it. That was the AI ML silicon gets created. And this is like a single instruction, multiple data kind of industry. Initially, GPU was used, but now there is a need of dedicated hardware to do training and they do inference also at a very low power. And that is how the market is looking at it. So there is a term called TOPS, and this is like a KPI or key performance indicator for the AI silicon, that how many TOPS it can generate for inference or for training. Memory side, SRAM, DRAM, NAND, NOR flash. This is like companies like Samsung, Micron, Hynix, Nanya. There are a bunch of companies who are making these chips, and these memories are going all over. DSP processor, ADC DAC, these are analog. Automotive side, we have, this is a in-vehicle infotainment, telematics, automated driving, automated driver assistance system. There are a whole lot of things are there. Nowadays, you can see that the cars can understand each other. It can read the lane disciplines, and it can understand the light, traffic signal light changing or not. You need a solid camera, you need a AI processing of that camera stream to make decisions, and that's what these automotive chips are doing. And in the early section, as it was told, this need to work in an extreme environment, because you can drive in Ladakh versus you can drive in 53.2 degree Delhi. So both the cases, it should work seamlessly without any issue. And of course, you need to provide power. So there are power management units, regulator chargers are there. And nowadays, the electric vehicles are coming, and the electric vehicles need charging. So you need these regulator chargers, which is taking a DC power. It is like a DC to DC control, you can say that. It is taking a DC power and providing the right voltage level to all these chips to operate on this. So if you look at the logic industry here, I think the top graph kind of shows that how it is distributed on various segments, like mobile phones. Just I'll go with only one. The way to read is that if you take a mobile phone today, about 28% chips inside are the logic kind of chips. There are 39% chips are like memory, and there are 33% in discrete, analog, and others. That's how you should read the top graph or the various way. So this data kind of shows that various kind of thing. But if you take a PC or laptop, 64% of the logic is kind of a digital chip. So now segment by segment, if you look at the mobile side, Qualcomm, MediaTek, Samsung, because the key ISP, the key item there is a modem innovation. They do a lot of modem innovation. They put the other things around it, and that's how they create a wireless chip. HPC side, Intel, AMD, NVIDIA, Here, the single throughput performance of a microprocessor is the key, and that is the key element, and they create a lot of other things around it. AI/ML side, Cerebras, Samanova, these are the new startups which is making a lot of noise in the industry now. And apart from that, you have Intel, Qualcomm, and others. Automotive, Qualcomm, NXP, Tesla, Mobileye, all these companies are there, and Analog, TI, ADI, all these things. So you need to understand that. To get into that, your logic sense need to be very clear. The problem solving need to be very much solid. You should have a good understanding of digital and analog electronics in your BTech courses. Ensure that you understand digital logic very well, your analog logic also very well, and of course, some amount of computer science will help, because nowadays nothing is done by hand. Once you understand how the digital circuits work, finally you need to run a synthesis tool to make a digital circuit. So some amount of computer science also help. Let's go to the next one, please.
Maybe I can take
So
it
from
up
this point,
here.
I'll just hand it over to Tapas. So Tapas, from here on, you can take it through.
Yeah. Okay. Thanks, Sumit. As you mentioned, that the SoC, system on chip, which actually has millions of transistors inside, you cannot really use every transistor to make such a huge chip. So you break down that huge function into smaller functions, and those smaller functions are actually IP or intellectual properties, because there are some design components in it where you design those blocks for a particular specific function or a specification. So it's almost like a human body. You have the entire body can be broken down into small cells, which can be called the standard cells. They are the foundational intellectual properties like AND gate, NAND gate, NOR gate, flip-flops, etc. You have the memories like SRAM, ROM. You have the standard IOs, which talks to the external world. So they are the foundational IPs. Then you have more complex IPs like the tissues of our body. They are called the SERDES, the serializer, deserializer, because you need to transfer huge amount of data from one chip to the another chip. And that cannot be done parallelly. So you serialize them, and on the other side, you retrieve the data. And that's a very complex function and a subject by itself called SERDES. Then you have those CPUs, like ARM CPUs, MIP CPUs, and x86 like Intel's CPUs. So they are also a kind of an IP because the CPUs are made separately. Then you have the video encoder, decoder, camera, image processors. Those IPs are also a complex function that are developed. Then different kind of communication peripherals, controllers, etc. They are also present, like USB, DDR, PCI. These components, it's not limited to it. These are just few list of it. There are huge amount of actual design content that goes in. That's why they are called the intellectual properties. And the SoC use these particular macros or intellectual properties, stitch them together, verify them, then place and route them, and form the SoCs that Sumit mentioned in the last slides. And the SoC companies which can finally fabricate them by themselves or by another house, which are called fab house. I'll come to that in the next slide. But in this intellectual property, I would like to mention that there are couple of streams of these intellectual properties that are present. Something called hard IP, which means you have the layout of the entire function, which is hardened and given to the SoC. They use just a view of that layout to interconnect the rest of the IP, rest of the SoCs to use that function. Then there are soft IPs where the IPs are written in Verilog, VHDL kind of RTL or register transfer logic, a language basically, and those soft IPs are integrated inside the SoC, and then they are synthesized and placed and routed, naturally auto placed and routed to be integrated inside the system on chip or SoCs. Then there are two different kind of IPs that are also used. One of them is called architecture licensed IPs like ARM. And one can license the architecture and implement their own way. And the other one, you can also license the instruction set and you can implement the whole thing by your own way. So they are also intellectual properties, but they are used and implemented in a different form. Then there are verification IPs because the SoCs are huge. I mean, it's a monster in the design. So you need to verify them very well. And so to verify them, you need to generate the test benches and those test benches, and as well as you need to analyze their the outputs of your design. Test benches and outputs are often not possible to generate by manual effort. Of course, they are done manually also, but there are verification IPs who generate those test benches and check their functions. The key players in this IP business are definitely ARM. Then you have MIPS and others who are into the CPU business. You have Synopsys and Cadence, along with their EDA. They do make standard cells, memories, SerDes, etc. Then you have AlphaWave, who focuses mostly on the SerDes business, and M31, who covers from foundational IPs to the SerDes altogether. There are multiple other companies like True Circuit, you have Analog Bits, you have MIPS, etc. And maximum numbers of companies, the startups are coming up in this field also all over the world. To get into this IP business, naturally, you need a deep design acumen in digital electronics. You need to know how the microprocessor architectures are, computer architectures are, as well as the analog design, means transistor level designs too. So now the question is, once you make the system on chip, using the IPs, using the EDA tools, where do they go? They go to the semiconductor factory, which looks like this one over there, lower right bottom corner. Actual silicon chips are fabricated there. They look like silicon disk with a lot of square sections, which are called dies. They are usually cut out, sawed out, and then you get your single chip. Usually these fab houses, they run through several chemical and mechanical and metallurgical processes. They are called diffusion, implantation, sputtering, etching, mechanical chemical polishing, etc. Finally, to form one disk of semiconductor wafer. And then in the next slide, we'll come to that. They are cut into pieces to form small dies, and then they are packaged. I'll come to that also. There are some critical terminologies that are used in the fab. Fab basically means fabrication factory, who actually imprints your design on the silicon. Then the key two terms are called lithography and EUV. Lithography is the method by which you imprint a transistor or an interconnect on the silicon, which has set of mask photographic mask, and then you have lighting behind it, and you smear the silicon wafer with a photoresist, and you pass the light through the mask, and you create different kind of patterns on that photoresist. Finer geometries become quite comparable to the wavelength of the light, normal light. So that's why to get onto the finer geometry, you need extreme ultraviolet light, where the lambda of that light is very small. So the accuracy of print on the silicon becomes much better. And you know that as you do it in such fine geometry, there are faults naturally occur, and you need to identify those faults, throw them out. So we will talk about that, how do you test and remove them. The effect is called yield. That means how many good dies you can cut out from a single wafer. The key players in this field are pure play foundries who do not do the design. They rent their house, their factory for the design houses to be fabricated. designs to be fabricated. There are the TSMCs, UMCs, SMICs, global foundries, and things like that. And then there are companies who are called IDMs. They make their own design fabricated in their own house, like Samsung and Intel. They also let others use their fab against cost, of course, to fabricate their chips. They are called fabricate the chips of the design houses who do not have their fab house. They are called fabless, like Qualcomm and Tapas. And then there are machines, very high-end machines that are needed to uh, to have this factory, to run this factory. They are supplied by companies like Applied Materials, Nikon, of course, camera, and ASML. If you look at the top left chart, which tells us different type of technology fabs, which are memory type of technology fab, logic technology fab, where you heard these different nanometer technologies from Jayantoda's very first slide, and you have discrete, analog, and others. So most of these fabs, if you look at the green one, is in Korea, and the orange one is in Taiwan. So major segment of high-end fabs are in Asia. Then there are fabs which are all over the place, like in lower geometry 2. They are also in China. Number of them are in US and in Europe too. So it's distributed all over the place, to be honest. Now, as we mentioned that we cut the cut the wafer into small dies. What happens to them? We package them. We put those dies inside in case, and the input outputs are taken up on the pins, and that you have seen as an IC. There are different kind of ICs over the year. We are not going to talk in details due to time limit today. So this packaging itself is a big technology because you need more and more IOs to have complex systems. The simple dual inline package or quad flat pack package evolves into ball grid arrays or BGAs, where you have thousands of pins which are connected to a package where the semiconductor die is within. Nowadays, you put more number of dies within a single package, and it's effectively a multi-chip module. A single IC will see a lot of dies from different technologies are put inside, CPUs, memories, analog components, all put together. Sometimes these dies are put over a big semiconductor piece, which are called silicon interposer. They're called 2.5D ICs. And sometimes they are placed on the package itself, like the green one, which are 2D ICs or multi-chip modules. The latest one in this picture is where you stack the dies on top of each other and connect them through a true silicon via to pass the signals. The analogy is like a landlocked country like Singapore, where you need to grow vertically. It's like multi-story building with lifts are the TSVs. So I'll not go into this picture. There will be a repetition. So the key package trains, I already mentioned that multi-chip, and you have the wafer level packaging also. And nowadays you will see most of the functions where the chiplets are getting integrated into the package, multiple chiplets coming from different companies are also getting into the package. So effectively what used to be in at one point in time a single PCB board, they are getting into the package. It's almost like that Hollywood movie, Honey, I Shrunk the Kids. The next one, as we talked about, that there are faults that are naturally formed during the fabrication process. And if you don't test them, package them, and send them to the original equipment manufacturers who are making TVs and computers and mobile phones and cars, and if the fault remains there, it will not work as needed, or sometimes it will be totally faulty. It cannot be. So you cannot really ship your chips without testing them to the greatest possible extent. So that's why we need to assemble and test them. First test is done on the wafer level. You find out the faulty dies, remove those faulty dies, package the rest of it. Then during packaging also there are faults developed. Then you test those packages again for all the functionality within, and then the good packaged components are only shipped. So you can imagine a huge SoC with millions of transistors inside. You cannot manually generate all the test patterns. You cannot manually check all their functions, whether they are working fine or not. So there is a huge discipline that has been formed, as well as a part of the ecosystem that has been formed to create all these test patterns and checking, or automatic test pattern generation and checking, as well as during design itself, you need to take care of in a certain way. So that particular field is called design for testability. That has to be done. And these two fields, automatic test pattern generation, they use the tools, automatic and design for testability are two major disciplines used in the SoC. And there's a huge demand for them. It's very easy for you to get into it if you have some basic idea of DFTs, you know, concept of digital design and analog testing. And then there are machines, of course, which are exercising those automatic patterns, pumping them onto the chip automatically in a robotized way, so that you can test them. Thousands and thousands of chips can be tested in few hours. So those equipments are also made by companies like automatic test equipment companies like Teradyne, Adjunct, etc. And there is a term that you will see now coming up called OSAT. It's outsourced semiconductor assembly and test. And you will be happy to know that the fabrication house and the OSATs, which are not there in India for last 3 decades, it used to be there in 80s. Somewhere we missed the bus. Something went wrong and we missed the bus. And again, they are coming back. You will hear, you must be reading them in the newspaper, that Tata is coming up with a fabrication house in western part of India, and there is an OSAT in Assam that will be in place very soon, maybe within a year. Now moving to the firmware and software, just to save the time, because Sumit already mentioned that one at a great level, I will just spare 1 or 2 sentences about it. There used to be a decade where you package the chip and you ship it. That's it. Your job is done. But later on, what happens due to this generic nature of the design, complex nature of the design, just sending the hardware, just sending the chip doesn't sell. So you need to make the system, the semiconductor houses, they make the system using PCB. They write different firmwares, they create the operating systems, and give an example to the original equipment manufacturers like HPs and the Bosch and all other companies that you see that lands up in your house. They use it from there onward. So I will not go into different segments of those software and firmwares because Sumit has already taken this one up at a great length. So I will move to most interesting part, where the industry is moving from now onward. In the design segment, if you see, of course, the AI is the era of AI coming in. So AI processors, in-memory compute, all those kind of things are coming up now. And there are applications like you do any kind of operation on your search or on your mobile that usually moves some data in the server. So there are server, the communication goes to the server by 5G, and of course the automotive where more and more electronic components are getting in. These are the part of the design and the system that comes in, as well as the technology. The technology has to advance in a great way to really support this kind of demands. It used to be a planar MOS geometry that you read even today, those who have the courses in the book. Then this technology called planar geometry, there's PMOS and NMOS, that for past 2 decades almost, we have something called FinFET, which is a 3D structure of the transmitter, of the transistor. and the FinFET now metamorphosed into a gate-all-around technology. All these things are happening. If you look at their the current carrying area is increasing and the leakage is decreasing. That's the main driving force behind this. And in future, there will be the CMOS, basically the PMOS will be at the bottom, NMOS will be at the top, a CMOS gate will be on the same vertical area. It's almost like, again, to say that multi-story buildings, even the chips will be, the technology will be a 3D technology by itself. Today, this technology is in production. In a quarter or so, this technology, you will see chips in the market from this technology. And by the end of this decade, you are going to see this technology too. Similarly, in the packaging technology, I already mentioned, you have, it's almost a city. If you open a package, there are single-story houses, there are multi-story houses. They are connected by TSVs, they're connected by roads on the package and the silicon interface. The semiconductor ecosystem will also, due to geopolitics, will also diversify now, because during COVID era, as Jayanta said at the beginning, during COVID era, we saw the semiconductor supply chain got stuck. So it is going to distribute, and keep an eye on India is also getting back onto this the semiconductor ecosystem. The last slide, just to give you an idea, because most of you are students or young professionals thinking of going for higher studies, etc. To get into a semiconductor industry, the first thing that you need is a basic graduate level fundamentals that has to be very clear on circuit theory, on CMOS circuits, on logic design, control systems, communication theories, and programming. You cannot live without programming any longer anywhere. On the master's level courses, the advanced courses, but they can be taken up as an elective subject by undergraduates too, to increase your chance to get into semiconductor industry. They are mostly advanced analog and mixed signal circuits. You have Verilog VHDL systems. They are sometimes practice courses or lab courses. VLSI technology, semiconductor devices like MOS structures, etc. VLSI testing and verification courses, and embedded systems. If you get some way of getting hands-on, because there are tools even in IIEST too, and in most of the colleges now, use those tools to increase your skill on synthesis, on schematic layout tools, on SPICE circuit simulations and logic simulations. The entry point to this industry for the graduates can be through internship, as well as for masters through internship. Of course, you can do masters in microelectronics and VLSI from different colleges, including IIEST, to get into the semiconductor industry. And if you want to go further, go for a PhD. That's not a must to get in. As a graduate, also you can get into this industry. With that, I believe we are just on top of the hour. Maybe we'll have some time for questions. I hand it over to John.
Thank you, Tapas, and thank you, Sumit. So I have a question for each of you. First one, possibly for Tapas. So, the scaling technology, right? We are now down to 2 nanometer, and then we are going to angstrom, maybe 1.6 nanometer, and this and that. So do you think, it's the end of silicon in the next few years, or you think some other technology is going to evolve?
Not really. Okay, maybe I just quickly jumping on because we just over the hour. Yeah, it is 2 nanometer, and some of the companies call it 20 angstrom. We got into the angstrom era from nanometer. And if you look at this picture, now still there are some real estate consumed, but you will see that more and more 3D kind of structures coming in. So on the same small area, you will have more and more packing density. And today, if you look at, we do have announced 14 angstrom. And I believe in a couple of years, there will be there will be beyond 14 angstrom also. It's not going to end so soon.
Thank you. So our jobs are safe. So anybody getting into the semiconductor space should not think it's the end of world. Thank you, Tapas. So one question for Sumit. Okay. So can you little bit comment on the Indian ecosystem, particularly on the design side, where we stand and your view?
Yeah, so Indian ecosystem, I think I would say this is the best time going on in Indian ecosystem because government is promoting various schemes to promote the Indian semiconductor side, and same time, a lot of the MNCs who are the experts, they also launched various programs. So on the government side, now there is a PLI and DLI scheme, which is like a production link incentive and design link incentive, where government take a significant portion of the cost they bear if the idea has a merit. It goes through a strict criteria. If you follow the criteria, then your cost is taken care. Government has taken the national EDA grid, where you can actually make use of the EDA licenses if you are part of that ecosystem, the DLI ecosystem. They have invested in a lot of universities so that the basic fundamental research can happen. So there are this is a lot of great initiatives going on, and good time for semiconductor startups also in India. Now, if you come to the corporate side of it, right, Qualcomm, we are running something called Qualcomm Semiconductor Mentorship Program. We're not funding a company, but what we are making sure that the startups can become a real company, and then we are taking it forward. Similar programs are done by NXP, by Intel, by Texas Instruments, and so many other companies. So definitely the design in India side, it is going, and also we just talked about that the fabrication, which was missing always, and the assembly and test, which was missing always. Now they are already there. There is a fab commitment in Gujarat, and there is a OSAT commitment in Moregaon, Assam. So there is a lot of things going on in the semiconductor side right now, and this is a very great time for India.
Yeah, so there's one question that has come in this chat. Very good question. So I do want to take that question. So Sumit, if you can answer this. It is from Arnab. It says, what would be estimated seed capital requirement for launching an EDA startup in India?
See, there is not a very straight answer to that. What do you need to launch a EDA? What exactly the EDA startup means? You need to know the algorithms and you need a computer. That should be good enough, to be very honest. But what is the capital getting used? Probably, typically EDA software run on a server. So you may have to rent out some server to try it out. You need to hire a few people. So basic cost is that the seat cost, what you need is towards that. So if you have an idea, if you're in a stealth mode, you can start in a very low cost point of view. And later, once you scale up phase come, once you go out and start selling your EDA tool for the various different companies, that time you start raising the fund. So I'll give one example of from one EM startup company. This is an EDA company um, by one IISc professor, Dr. Dipanjan Gop. He started that company in IISc lab, which does the EDA simulations and EM simulations. And what is the application area? Any device which is impacted by EM, like even the automotive and other space. When they started, this company started in IISc lab without any basic bigger funding. They recently raised their Series A funding for that. So if you see that, if you have a good access to the server and if you have a good algorithmic sense, then for the space of EDA, it is not going to limit you. The big fund is not going to limit you.
Thank you. I think we are almost coming to the closing of this session. Thank you for attending. What's more important, all of you who are part of that WhatsApp group, right, on Semiconductor Special Interest Group, please let us know what all topics you'd like to hear from us, right? And we have experts from every field, I guess. I mean, there are so many BE College IIST alumni working all over the world in various top-notch companies of semiconductor, so we can pull in all that resource. So it depends what interests you and what you like to hear, right? With that, I will close this session. Thank you very much for attending it, and we hope to share the recording very soon. Thank you all. I'm closing the meeting now.
Thank you.